In this video, I present to you ClusterXplain, which is a tool to compare root cause analysis pipelines in finding the scenarios in which a computer vision DNN may fail. DNNs are used in safety-critical systems like autonomous driving for tasks such as lane and object detection. In these safety-critical systems, the margin of error is extremely thin. A single wrong prediction in a safety-critical system can lead to devastating consequences. That's why understanding why DNN makes certain errors becomes crucial in these environments. However, we may have a lot of input leading to failure, and inspecting them all to identify what are the failure scenarios could be difficult. Our idea is to group together similar error-inducing images because they capture the same failure scenario. For example, this cluster represents images that failed because the images are too dark and blurry. To generate root cause clusters from the failure-inducing images, we rely on a pipeline that has three components. The feature extraction component extracts the features from the images, and then the dimensionality reduction component reduces the sizes of these features, and then the clustering component generates the root cause clusters. After generating the clusters, the engineer inspects each of them to understand the root causes of failure. We explore variants of each component. For feature extraction, we use black box approaches. The black box approaches are the transfer learning-based feature extraction models that rely on pre-trained image classification DNNs to extract the features. For dimensionality reduction, we study the effects of using the features without reduction and also reducing the feature dimension using PCA and UMAP. For clustering, we use three well-known algorithms: k-means, dbScan, and hdbScan. This results into 36 pipelines. We use an attended child detection case study from our partner RE Sensing, which is DNN that detects whether the child is left unattended in the backseat of the car. To evaluate the ability of our pipelines to generate clusters that represent failures of the DNN, we need to know which are the root causes of failures that are present in the dataset. We modify a subset of images by injecting features corresponding to a failure scenario. For instance, we add noise to the image, or we add an everyday object in the backseat of the car. In the second part of this video, we will demonstrate our tool ClusterXplain. To run the tool, you have three options. First, use a pre-built Docker image. Download the Docker image from our repository and upload it into your environments. Then run the application with a single command and access it through the interface in your browser. The second option, build the Docker image locally. Clone the repository, then build the Docker image following the instructions in our README, and then start the application. The third option is setting up the environment from scratch. First, install all the dependencies following the README in our repository, and then run the application using the following command. In each case, once the tool is running, you can access it into your browser at the provided local link. The tool takes as an input a folder containing failure-inducing images. Each image is processed independently to extract features and identify patterns. The images should be in standard format like JPEG or PNG. Through the GUI, the user configures the analysis pipeline by selecting the feature extraction model, the clustering algorithm, and the dimensionality reduction method. After selecting the components of the pipeline, the user clicks on the Run Pipeline button to generate the output. After the process is completed, the output is displayed below. ClusterXplain provides quantitative metrics to evaluate the quality of the clustering. These metrics are the silhouette index, which measures how closely related the data points within the clusters are, and the Davis-Boulder index, which measures how well separated the clusters are. Images from each cluster are grouped into animated GIFs and displayed here. These images offer a dynamic way to inspect clusters. Each GIF cycles through the images belonging to a specific cluster, making it easier to detect shared characteristics or anomalies within a cluster. For example, in this cluster, these images failed because they are too dark, And the images in these clusters failed because they contain noise. A 2D scatter plot is also created to visually represent the clusters in the reduced feature space. The plot helps user identify visually coherent clusters. ClusterXplain allows the user to compare the performances of the different pipelines. If the different quantitative measures or the UMAP projections show that the images are poorly separated and not well grouped, or if the clusters contain images that differ significantly from one another, users can pick a different pipeline using the same interface and then click on the Run Pipeline button. The second pipeline only generated 3 clusters, with the higher value of Davis-Boulder index, which shows that the clusters are not well separated, and the lower value of silhouette index, which shows that the images grouped into one cluster are not well related. We also notice that in the clusters, images that represent different failures are grouped into one cluster. The UMAP scatter plot shows that some clusters that need to be separated are grouped into one cluster, and clusters that need to be put in one cluster are put into 2 different clusters.